Hello, welcome. My name is Charles Scrillo, and this is an introduction to IoT pen testing. So for the agenda today, we're going to give an introduction about myself. We'll talk about the basics of IoT security. Then we will define what's known as the IoT attack surface. We'll look at things like the NIST cybersecurity framework in the IoT space. We'll look at a framework for testing these devices, known as the OWASP IoT Top 10. We'll talk about a concept known as the -1 ring in IoT. We'll discuss some wireless topics regarding the Internet of Things, and then we'll talk about some tools of the trades and some examples. So again, a little bit about myself. I am the practice lead at Chrysler Miller. I'm also heavily involved in USA roller sports, outside of technology, very heavily involved in hockey. From an IT background, I've been a red team penetration tester, physical security specialist, a certified ethical hacker, CISSP. One of the founders and main members of Philadelphia Security Shell. So that's a club that meets at Drexel and goes over, everything that us geeks nerd out in our basement, things to that extent. And I also teach at Drexel University. So where to start? When you look at IoT pen testing, there's really no clear cut. Here's the path to follow. So I was a little bit confused. So I started going back to the basics. So this is, quote unquote IoT security, but this is just the basics of security at a fundamental standpoint. So what's the privacy of the device? What's the encryption? Major weakness in some of the IoT is how they authenticate. Do they have the ability to even multi-factor or regular authentication? Integrity, something like a secure hash, and our simple non-repudiation or our digital certificates. So what does NIST have to say about IoT and the IoT threat landscape? Major concern regarding the lightweight encryption, if any at all. Huge concern over cybersecurity for our physical systems, so our SCADA networks, things to that extent. A very interesting term I've been hearing around the space in the government sector is this concept of electromagnetic agility. And what that is we do a lot of good things well in certain parts of the spectrum, 2.4 and 5 gigahertz from our Wi-Fi. But we need to do the same type of security and the same type of controls across other areas of the wireless spectrum. For things like wireless medical devices and IoT-based distributed threats. What does that mean? So because of these IoT-based devices, we're seeing now, distributed denial of service attacks through webcams or IP cameras, things to that extent. And one of the oldest portions of IoT security is RFID security guidelines. So again, pen testing IoT 101, where to really start? Like any pen test, even if it wasn't an IoT device, we would start with what's in scope. What is the client? What is the institution, the organization, etc. that we're trying to baseline? What are they looking to have evaluated? Is it simply the wireless communications of the device? Is it the device itself? Are they looking for a physical penetration test on the device? Are they looking at an application layer at the mobile or cloud-based? So there's a lot of different avenues when you look at what we're going to test or what's in scope from an IoT device standpoint. So one of the first things you need to know is, what's actually going to be what you're evaluating. Because once you have that, you can start to create, your IoT testing roadmap. And one of the interesting parts about the IoT device is, who's the SME? Who's the person that is the product designer, the technical nuance, someone that took this device that necessarily wasn't always internet connected before and is now adding some internet capabilities to it. Have to have that technical discovery, have to really understand what was the purpose of this device and what's it really meant to do, and how could someone, knowing that, maybe abuse what it's designed to do. Then we'll look at the attack surface, and we'll review this as our OWASP IoT Top 10. With that framework, you could begin some technical testing. And one of the interesting parts about the IoT space in general is this concept of vulnerability ranking. So in a traditional pen test, at some portion of vulnerability assessment, you'll run Nessus, Qualys, you'll run your vulnerability scanner. And it will give you back your list of critical high, medium, lows that you'll include in the report and remediation steps, all that good stuff. But in IoT, there's a real concern on how we're ranking these vulnerabilities per what is the vulnerability on the device. Is it jammable? Is it susceptible to capture replay attacks? And where does that fall within a risk matrix on what the device is supposed to do and how it's being abused? And then like any pen test or any security assessment is the reporting. So what is the IoT Top 10? What's OWASP? So OWASP, our Open Web Application Security Project, they created an Internet of Things Top 10. So they have the IoT project, and what we're going to walk through next is the various attack surface areas. And what's been coming to the surface recently is some testing guides, some top vulnerabilities, but that's where we're at in the IoT space and what we have an ability to test. So what is in the IoT Top 10? So first and foremost, the insecure web interfaces a lot of these IoT devices are interacted with through the web. So you're going to want to incorporate the entire OWASP web app Top 10. So they, outside of the IoT, they initially got started as a project creating that web application Top 10. That's full scope as far as number 1 in their IoT Top 10. Interesting one is number 2. Insufficient authentication and authorization. So sometimes there's just a lack of password complexity. The device can only handle a 5-character password, things to that extent. Insecure network services. Like any device, if this device has services running, are they vulnerable to denial of service or a buffer overflow or other network level attacks? Transitioning right at the network level and looking how it's transported across the network. Number 4 is lack of transport encryption. So a lot of unencrypted services. Sometimes if there's encryption, it's proprietary. If there is encryption, there's things like SSL pinning not being done on the certificate side between the mobile application and the server, things to that extent. Number 5 is going to be a very interesting concept regarding GDPR. So what is the privacy concerns of the device, and what's it storing, and where is it sending it, and how is it collecting it? And that's going to be a major concern in regards to that European data regulation when we look at what's actually on the device and how do you forget the light bulb, right? Insecure cloud interface. So there's been a lot of interesting research and talks at Black Hat and DEF CON last year regarding not necessarily looking at the mobile application or the device itself, but going directly to the server side and do things like brute forcing account numbers and passwords, things to that extent, where if you knew that you were given guest level access to, we'll say, a smart lock, if you knew that information, you could go back server side and start changing the parameters, maybe get the lock to open remotely, even without needing the mobile application itself. Speaking of the mobile application, number 7 is going to be the insecure mobile interface. So again, more credentials in the clear, not being encrypted to and from this IoT hub concept that we'll discuss. And a lot of things don't have your generic account lockout, so they can be brute forced or easily guessed. Insufficient security configurability. So, how do you push the IoT device to a syslog? To something to that extent is how are we going to understand what's actually taking place on this device or to this device, and how would we mitigate that from a security standpoint? Number 9 is insecure software and firmware. So whenever these IoT devices get updated, there's a lot of sensitive information sometimes in the firmware of the device that's being updated. How that process takes place is of high concern from a security standpoint, because if someone has the firmware, as we'll discuss later on, there's plenty of tools and techniques to do some pretty interesting things to that binary file. And number 10 is poor physical security. So again, when you're creating an IoT device, you have to assume compromise because the adversary will be able to go buy your product and get their hands on it. So poor physical security is a major concern, and that's what we're dubbing at KM, and again, this is an official term, just something we came up with, is this -1 protection ring in the Internet of Things. So we're familiar with this picture, this graph here, CISSP level 1, where we're going to talk about the rings of access control and the different levels of control: application, device, driver, etc., kernel. But what's past the kernel is the actual hardware itself, and that's again what we're dubbing this -1 protection ring. You have to assume, as an IoT manufacturer, that your device is going to be in the adversary's hands. So you have to plan your engineering process around the fact that they're going to take it apart. They're going to try to look for poor physical security and extract the firmware, things to that extent. So you have to take that into the engineering process and your QA. So again, IoT really brought back the concept of the mesh network. And what that means is, you see in the picture, we have all these different sensor-based technologies that are communicating with different wireless protocols that we'll discuss, but they ultimately end up at the hub. And that hub's that device that ends up being plugged into the router and actually communicates over TCP/IP so that your phone can get that alert that the door or the window's been open or closed. So one of the interesting things regarding these wireless protocols, and something that's made IoT penetration testing very interesting, is the concept of software-defined radio. Just like we have software-defined networks, software-defined WANs and LAN, all that good stuff, same concept in the radio space, where we don't need a lot of hardware anymore. We need one piece of hardware. And with that piece of hardware, we can tune across this entire spectrum. So we have a video at the end of the presentation of us being tuned into 433 megahertz, which you can see on the left is your remote control or your car key. We know that our medical devices are going to be in the 2.4 gigahertz band. A lot of them, some of them fall below. So there's, as you can see, with one piece of hardware, either a hack RF or a blade RF, we'll go over what the difference in those are, you're able to analyze this entire spectrum. So what's some of the basics of this concept of software-defined radio, and what are some of the things you need to know? So when you're using a software-defined radio, you are capturing this wireless signal in the rawest form. So now we're going to kind of go back to Engineering 101 and really talk about digital modulation is what this comes down to. So a cycle is how often the signal is seen, and the cycle per seconds are hertz. So when we talk about gigahertz, you can see the baseline here of how quickly this wave's traveling. And the distance between the waves, again, is the cycle. Next, outside of those couple terms, is the amplitude, or the vertical distance between the crests. So how often are we seeing this signal? When we do see the signal, how big is the waveform? And this is what you're capturing with a software-defined radio. So some of the things you'll have to understand is this idea of modulation. So we have our digital data that's being represented here at the top, but how are we actually getting across what's a 0 and what's a 1? Sometimes we'll use amplitude. So we will simply, 0 will be no signal and 1 is a signal. That's very popular in what's known as on-off keying, garage door openers, things to that extent. Frequency shift keying. So are we going to change how often we send the signal to the device to communicate or differentiate again in our modulation schemes between a 0 and a 1? And our phase shift keying, which is going to be the differential of sine and cosine. So as you can see, the waves take a very big form to show a 0 and a very small form to represent 1s. So again, here's where some of these modulation schemes end up. They'll end up in things like ZigBee with what's known as offset quadrature phase shift keying. Bluetooth Low Energy and Z-Wave are using Gaussian frequency shift keying. And your doorbells, your lights, simple smart devices are going to use amplitude, or sometimes referred to as on-off keying. So one of the first wireless protocols we'll take a look at in the IoT space, and this is heavily used in physical security, and again, those low-level sensor-based, is this protocol known as Z-Wave. And Z-Wave was, again, designed for the low latency device-to-device communication. So at the physical level, you'll tune your software-defined radio to 908.42 megahertz. So that's going to be the average stateside. What frequency channel at the physical layer you'll have to listen on. Then once you capture at the physical layer with our software-defined radio, you'll see in some screenshots we have later in the presentation, you can actually pipe that traffic directly in the Wireshark and interact with these packets as if they were coming across through a regular Ethernet connection. So what's inside of this Z-Wave packet? And this is what's very interesting, and this is a great packet to take a look at what's really happening under the hood of a lot of IoT devices. So because these devices use carrier sense, multi-access, collision avoidance, long, complicated term for, they'll ask permission before speaking on the wireless wire per se. So because of that, A, they're susceptible to jamming, and B, because these IoT devices are speaking so infrequently, they need to initiate communication. So the preamble is this signal where, okay, we've gotten clearance to talk on the wire, and I'm going to talk to this other device, and I'm going to send a bunch of A's or some sort of value to say, hey, there's a frame about to start. So we'll move into the start of frame. And then I'll actually send my MAC data frame, and then I'll end that frame. And because of IoT devices and the way they're mesh networked, we look at this single MAC frame, and this is very interesting as far as how these packets get around. So there's always the home ID, and that's going to be the entire network of IoT devices that are interconnected. And then we still have our source and destination, and then our data payload and the checksum. So what's in the data payload when we're talking to an IoT device? Again, these are very low data points from a packet. There's not a lot of information in here, so what's getting communicated? We have the header of the packet, and then we have this concept of command class, which would be, if we're going to use, we'll say, the Philips Hue or the light bulb as our example, the command class could be something to the extent of light bulb configuration, where we're changing the configuration of the light bulb in real time. Next would be the command, so light color. And then our parameter, simply, are we changing this color from red to blue? As you can see, there's not a lot of information that travels across these packets. The next wireless protocol we'll talk about is 802.15.4, better known as ZigBee. And this is an interesting protocol because it was developed, again, like all protocols at the IEEE level. We'll listen to 2.4, which is what most ZigBee devices are operating on, is that ISM band, or they'll operate at below a gigahertz in either 915 or 868. Once you get past the MAC layer of the ZigBee protocol, there's a lot of different interpretations on how to use this protocol. Because it was designed for the IoT device, as you can see, there's concepts of the ZigBee Alliance, which is simply the software or the application layers. A lot of times, individuals developing these devices will only get to the network layer and then create different layers of encryption, things to that extent in the security layer. So the Alliance doesn't always define how you implement your ZigBee device. It's a lot of best practice and various vendors contributing. So what's happening under the hood of your traditional ZigBee packet? So one of the things that was corrected in ZigBee and has later been corrected in Z-Wave, but what was missing is a lot of encryption. So when you have to encrypt a ZigBee device, you have to understand that, A, we're going to mesh these devices, so they're going to be able to talk to anyone on the network, but they also are specifically meant to talk from one link to the other. So the network key is the encryption key that you're going to use across the entire IoT landscape, or from the hub in on your IoT network. And then the link key is going to be from one light to the other, or from one switch to the other light switch. It's not going to be, again, across the whole network. It's device to device. Its limit is 2. Major security concern here on how you deliver these keys. There was a major hiccup the first time or go at this when we delivered the network key as A, being static, and B, being unencrypted. So someone was able to actually capture early on in the IoT light bulb lifecycle this network key, and it worked across all the IoT light bulbs that were ever sold from the manufacturer. So there was a major firmware upgrade to fix that. Again, with ZigBee and all these wireless protocols that we're discussing, if they're only talking when they need to, how could they ever alert if there's jamming taking place in that frequency channel? Because of the lack of complexity of some of the packets, can you capture and replay that unlock or on or off code, etc., and it's just going to work? There's no checksum, there's no integrity, things to that extent. Or is there a couple things that are inside the packet that we could modify and still ultimately replay it and be able to expose the device to some vulnerabilities? So again, there is the process and there is the capabilities, and this was something that we discussed at this year's Comcast Internet of Things Security Conference, was this concept of real good AES encryption over the ZigBee protocol. And it is possible. There's something known as the elliptic curve Diffie-Hellman, and this is made possible, and we won't get too much into this, but basically this Davy-Myers hash that's being utilized in this version of the AES encryption is very lightweight for these smaller devices, so they're actually able to have a full structured AES encryption process without the overhaul that it traditionally exposed them to. So Bluetooth low energy, we mentioned that it's going to be in the 2.4 ISM band. One of the interesting things about the Bluetooth low energy is that it has advertising channels and then communication channels. So you'll advertise at 37, 38, or 39. And you'll negotiate what's going to be your frequency hopping scheme, because what's interesting about Bluetooth low energy is it doesn't stay on the same channel for very long. It will hop across the spectrum or across frequency channels and delivering the data packet. And this is of concern when you look at testing the devices, because you can't listen to a specific channel. If you think of Aircrack NG or the wireless pen testing suite, where you would tax C, and then 11 would be, well, I want to listen specifically to channel 11. There's a device we'll talk about a little bit later called the Ubertooth, and this device is going to allow you, again, to listen to all these channels at once, and then with your on-board Bluetooth card, interact at certain different levels of the communication. And from a visual perspective, this is what we're talking about when we say adaptive or frequency hopping. So we have two different links or two different lines of communication, and we have frequency and time. And as you can see, they're not communicating on the same frequency for more than from one packet. So there's a frequency scheme that you will communicate with the Bluetooth low energy device on what channels you're going to hop in, what order, and that's part of that negotiating when you first pair the device. RFID. Very popular in our access control, smart animals, where we're herding cattle and things to that extent through RFID and being able to track these devices in the actual animal itself. So there's a lot of still very good use for radio frequency identification. Product tracking, again, everyone gets in the door with these cards, but they're still, again, vulnerable to not being encrypted, capture replay, things of that extent. So going over a good high level of introduction to IoT pen testing, what's wireless communication 101, what's modulation. So what are some of the tools and what's some of the pen testing examples that we have from some of the research we do in our cyber lab. So before we get through any of the examples, kind of give a quick slide of what I've been using and what's a tool set, what's the IoT pen test bench look like per se. Ubuntu is going to be the most popular operating system. If you're a pen tester full-time, you can get all these tools in Kali, but you're going to want to use a dedicated machine because you're connecting the software-defined radio directly, and you're going to be doing a capturing with that. Connecting that into a VM will work for certain demos and things to that extent, but when you really get into the weeds, you're going to want a dedicated machine. The Universal Radio Hacker is a great front-end tool for managing all your software-defined radio capture, replays, modulation schemes. It's a project organizer for your software-defined radio. Also as a front end for interacting with how you're going to build your software-defined radios, which is GNU Radio. So this is the software platform where, again, you have one piece of hardware, and then through the GNU Radio, you will make your physical radio in software that will modulate, demodulate, and do the rest of what you want to do to that captured signal. Anytime you're going to want to get in the middle of the traffic, from a cell phone standpoint, man-in-the-middle proxy, web application, still using the Burp Suite. Blue Hydra is going to be a Bluetooth low energy specific tool. Killer B is for ZigBee. Binwalk is going to be a binary file analysis tool that we'll discuss. Firmidine is going to allow us to emulate any binaries that we're taking a look at with Binwalk. And the APK tool is for reverse engineering Android apps. So that's our OS software. Hardware is a HackRF. So the HackRF can send and receive from a data RxTX standpoint. It can't do both at the same time. So you either have to have two HackRFs to be multiplex, or you could buy a Blade RF, which is going to give you that multiplexing capability. Yardstick 1 is an official software-defined radio for everything under the sub-gigahertz channel. And Killer B that we mentioned in our software is going to be utilized with this Amtel RZ Raven USB dongle, and that's going to be something that allows us with some custom firmware to send and receive ZigBee packets. Ubertooth 1 is going to be in the ISM band of 2.4 and it's for Bluetooth low energy. Our Proxmart device is for RFID. Our JTagulator is for the number 10 on the OWASP is going to be if we're going to physically extract information from the hardware itself. How do we know where the JTag pins themselves are? How do we identify them? The JTagulator is going to be a device that you need. Every cable adapter you can think of, your basic PC build and repair kit, you're going to be some modding. And if you're married like myself, a lot of my research gets done after hours, so a patient wife. So what's Binwalk? We said it's for analyzing the binary images. So even if you were, for say, an example, be able to go to a website and download the firmware and then flash it yourself, what could you do? What could you learn about the device from having the firmware, in your possession? So Binwalk's going to be a tool that lets you extract the firmware into its rawest form, or its Squash FS, which is all firmware is a subsystem of Linux that's zipped up a certain way and then flash the device. So once you extract the firmware and actually start digging into it, you'll have some pretty familiar folders like Etsy. So in this example, we have a D-Link router that we're navigating into the Squash FS root, so the unzipped file system of the firmware. We've navigated to Etsy scripts, miscellaneous. We came across a telnet script that we simply catted. And if you see in this telnet script, the image sign variable is simply a cat of a static file, or what's better known as a hard-coded password. So ultimately, what we're able to extract from the firmware itself of this device is that password you see at the very bottom, which is going to be a hard-coded password that was inside the router itself. So again, the APK tool, you simply point it at the APK file or the Android app itself, and it's going to reverse engineer the app and give you the ability to locate some keys. So this is a very easy way of locating API keys, API calls that this IoT device might be making. So this is a quick screenshot of after extracting the Android application, you're able to go in and actually see what are some of the keys and authentication points that this device would actually use when it goes server side. So again, Firmidine is a very interesting tool because back to our downloading the firmware off the internet, let's say you don't have a physical or a hardware version of the device, but you still want to try to analyze it from an IoT pen testing perspective. Firmidine is going to emulate the binary in real time. It's going to emulate the non-volatile RAM. It's going to do everything to spawn this device as if it was physically in front of you. So you'll get a web address to navigate to and get the Linksys router, whatever you're troubleshooting or testing, without needing physical hardware at your station. So this is a very interesting tool to use in the IoT pen testing space. Next concept, or one of the things we discovered in a lot of our IoT devices that we tested, is this concept that we're dubbing the IoT onboarding. And this is a process that a lot of IoT devices undergo, and it's still a major vulnerability, even though it only happens once. It still happens and can be captured, and how frequently we're introducing these new devices. Every time you join a light bulb or a light switch or a fridge or a freezer, anything, it goes through a process similar to this. And what happens is you plug the device in, you power it on, and it opens up a wireless access point for you to connect to. That's open. So the first thing we tested in the open access point, well, is there a limitation on how many computers? And that's a no. So we could join, we had, for example, 12 placed devices on this wireless network that was simply the Netgear extender, we'll say, for example. And you join the open access point of the extender, and then you go to navigate to google.com, and you get a splash page. And the splash page says, let's register this IoT device to your actual wireless network so that we can communicate out to the internet. You can check the status of your light, etc. What you have here in this screenshot is an example of every single IoT device we tested that walks through this process. Again, it's an unencrypted JSON post to the router with the username and password that you're putting in to register the IoT device to the network. So that happens every time you join a device to your network. Someone else has the potential to listen and capture the corporate or private credentials. Here's a great screenshot of the Universal Radio Hacker, so you can see the tool's color-coded. It's letting us define what we believe to be the preamble. What's the sync word of the packet? Where's the actual datagrams? Things like source and destination address are easily observed and analyzed in this platform. And again, it's the front end for interacting with your software-defined radios. And it lets you inject traffic right back to the device. So we have a video later of us using the Universal Radio Hacker to unlock a car. So we've talked about GNU Radio a lot. We talked about building out our radio in the software space, but then using one piece of hardware to interact with it. This is a quick little screenshot of what that looks like. So we're defining a source for the software-defined radio. We're bringing that source of data in, and we're going to use a certain physical modulation scheme. Then when we get to the MAC layer, we'll define it as ZigBee or 802.15.4. And we create different sockets, and we can sync the information. But what you can do when you start playing around with these radios is pipe the information you're capturing with your SDR right in the Wireshark. So here's a nice little PCAP that we took a screenshot of us interacting with an IoT hub that had a lot of ZigBee devices. After analyzing all the ZigBee communication, it was clear that security was not enabled in any of the mesh device communication or mesh to hub communication. So again, one of the oldest things I came across as a pen tester early on in my career that got me into the IoT space was the access control system. So again, I mentioned earlier in the presentation that I have a background in physical security. So breaking these devices on a couple early engagements in my pen test career really got me interested in this IoT device, or this device that is sitting on the network and is getting an IP but can't have things like AV installed on it or things of that extent. So one of the interesting stories we have about a pen test and an access control system is the idea of, real quick, we'll go back, is you need to have the whole device that handles the access control or the database, the content management. So this application server that you see here in our picture is what we were trying to find on an internal pen test that we had gotten physical access to, because we didn't know how long we were going to have access, and we wanted to ultimately be able to come back at a later time at our own convenience. So long story short, we were able to call the manufacturer of this control system, and they gave us an EXE that we could run on the network, and it would discover that panel for us, or that access control database system. Once we had access to that system, like most of the IoT devices, it was telling us where all the cameras were, and they're not encrypted. So now we have access to see everywhere into the building. With a quick Nmap scan, we can then connect to those cameras and have real-time insight to where we're at in the building and who's coming where. Next would be interacting with the device itself, or the access control appliance. Turns out, per that call or that help desk ticket that we opened, that there's a hard-coded API to upload or download cards. So once we realized that, we were able to dump the entire card database from the access control system, add our own card that, as you see in access level 2, has the front entrance disalarm always, and basically what that allowed us to do is come and go at any time after hours, and it would disable the alarms. It wouldn't notify the cops to that extent, and then we could present that card back at the door when leaving, and it would do the same. It would reinitiate the alarm, etc. So automotive security, all these different IoT devices that we discussed, they keep getting plugged into vehicles. We have 4G LTE cars that were talking over Bluetooth Low Energy as keyless entry systems, all that stuff. What's it look like from a security standpoint? So a while ago, when software-defined radios really started to take off, someone figured out that there was this concept of the golden key. So basically, at this point, with our software-defined radios, we can tune to car keys, or individuals unlocking their vehicles. Pre-2013, if you were to capture that car signal or car key signal unlocking the door, it was for life. It didn't need dual factor. There was no thing, as you see, a rolling code. There was nothing to defend. So the car industry created the rolling code, or their version of dual factor, where we're going to send the unlock or the static code, but then we're going to append a once-only rolling code. With anyone that's ever been in a parking lot, the reason the rolling code system's broken is if for the truly be dual factor, we would only want to use that token once. If that were to be the case with our car key, if you ever tried to unlock your car and you were too far away from it, you would then, quote unquote, forever be locked out. So what they did is they created this rolling code concept, but they could become interchanged. There was no certain order. It would just only use the value once. So what we can do with two SDRs is we can jam on a certain frequency, as you can see the jamming window, and then with the receiving window, we can capture the car key. And what we do is we capture 3 keys. We replay one to the vehicle, so the individual gets into their car. They can go about their day's work. They come home. But us as the adversary still have 2 working unlock codes, and we've seen this a lot. A lot of CNN, a lot of Fox News stories in major cities where cars are getting breached or unlocked and everything's being emptied, and they can't really file the insurance claim that did you leave the car unlocked. It took a while for law enforcement to realize that this is what was actually happening. So here's a video demo of what's known as the RollJam attack. So that's how quick, that's how easy using a software-defined radio, universal radio hacker, and something else to, again, jam while you're capturing on a little bit lower of a frequency. That's how the RollJam attack works. One tool that I wanted to talk about in particular with the IoT pen testing is this tool called Vapor Trail, and I've dubbed this, data exfiltration of tomorrow. So this was released at this year's DEF CON, and this tool is very interesting in the fact that we've always, if you're a pen tester listening or had a pen test done, they're going to try to get the Dropbox in, or that Raspberry Pi that's going to be implanted on your network and then communicate back to the CNC and give the tester, permanent remote access. Well, one of the things that people are getting better at is understanding what's leaving the environment. So our egress security has really matured over the past decade, we'll say. But so this is a total new approach to getting information out. So what Vapor Trail does is you plug the Raspberry Pi in. It's auto set to run responder in our story. Responder's a tool, if you're not familiar. It's going to allow us to quickly create authentication portals and capture Windows hashes. So now we have a bunch of Windows hashes that we're trying to exfiltrate. And we can't get it out over traditional TCP/IP. So with Raspberry Pis, they actually have a built-in FM radio antenna. So what someone figured out and presented at DEF CON is that you could send over FM modulation the responder hash file and then capture it in your car or some other device that was running the software to find radio. So none of your intrusion detection systems are going to be able to spot malicious traffic in the FM space, right? So this is data exfiltration of tomorrow. Be very interesting how attackers adopt this type of technology in the way they exfiltrate data. So again, thank you for taking the time. My name is Charles Scrillo. I'm the practice lead at Chrysler Miller's Technology Solutions Lab, and I hope you enjoyed the presentation.